Hi guys, so I am Ali Farhan. I am PhD fellow at Chung-Der Christian University, Taiwan, under kind supervision of Professor Chung-Der. So today I would like to present about the basic and simple program initiation, installation, and the processing of the measurement regarding for the blood flow velocity of blood flow velocity measurement in zebrafish and medaka. This is OpenCV based approach, and I must say some brief introduction that we have approach in our lab, and we already have developed the OpenCV based measurement for the cardiac analysis, as well as we are very good in providing to target the approaches that are cost effective for the measurement of the blood flow velocity as well as the cardiac rhythm. So we target to provide our best in research and development, and also especially in the area for the animal modeling and zebrafish. So this is the introduction that you can see our OpenCV based approach that comprised related to the artificial intelligence, and this is the era regarding the most of the confined algorithms are being designed. So we simply use the OpenCV approach for the automatic blood flow velocity measurement in the zebrafish and medaka by using the concept of optical flow. That optical flow is well established and well recognized, especially in the concern of the smoothing landing of the aircrafts, and also in the defense system of the radar system that has pivotal role. And the most commonly practicing optical flow algorithms, Lucas, Kennedy, Gunnar, Farneback, and you can search more about that. And also by using this approach, we analyze our tool by comparing for the result that we get in the our previously developed method using ImageJ software. So because every time we need some validation, so as well as we already good enough for the ImageJ processing, so we did compare our result from both fish data, blood velocity, by using ImageJ. And then you can see about the most of the concerns that are involved our setup. We have automatic blood flow velocity analysis zebrafish medaka that we use for the processing, and simply you have 2D videos recording that must be of the dorsal aorta in this case, by using high speed CCD and installation of the Python 3.9 language. And also it is essential to download the necessary OpenCV based packages. I will show you the details in next slides. And simply you need to install that by command prompt window and access the folder that you created on your system by using whatever the title or the path you used. And then is the video open in the MP4 format for the Python. And it is necessary that I mentioned here for the use the command to run the program and press option 0 for zebrafish and 1 for medaka. This is the point that you must be careful, and because two separate scales are mentioned in the script that will be executed if you select the respective option. So 0 is for the zebrafish and 1 is for medaka. And by using the cursor simply on the window that opened with the video, you will next automatically will see the ROI selection for the location of the dorsal aorta that will be presented in separate window. And by this feature you can say there is no need to select manually ROI for every time if you need to perform the analysis. And then simply opening the command prompt window. So the you here you can see we have the setup, a high best video that is traditional for the resolution and the exposure time and auto short speed, record frames, preview, trigger stop, that based on the resolution for the size of the video that taken, with the linear correlation relative to the sharpness. And then the exposure time that mostly concerned with the time of the light with the sensor, and also auto speed concerned with the number of frames like 30 or whatever. And also the record frame, that number of frame that we record actually on the real time, and the record time that must not be exceeded with the maximum limit of the frames like in the case of 0. And preview, you must have the condition like interest of the under microscope object what you have. In this case we have fish, and then you will be see the trigger that is to start the recording. And then steps to initialize the program. Here we have simply you put the mp4 video in the folder, and as I mentioned earlier, Python 3.9 create folder with whatever name you assign, place zebrafish or medaka dorsal aorta videos for the blood flow analysis. Simple command prompt window you use, and no need of GPU. The average CPU system can enough for the processing of this program, and no use of anaconda prompt. The simply command window is enough to proceed this. So this is basics, simple. We all already mentioned that we prefer for the easy and user friendly and cost effective approach for the detection and the automation processing of the analysis to contribute in the relative fields. So other is like that in most of the cases we have different environments in the system like using anaconda and that, so you do not need for that. So necessary commands that you must is to import the libraries like pip install python. Basically python is for the initialization of the your front window that mostly you can see in the programming used for the specificity of the display, but most concerned it is related to the GUI. So this is not the that GUI, but used for the display of our windows that I mentioned later. And then installed OpenCV Python module that is built in, you can already mention, and pip install with step. This is the for stabilization of the video, and we included this feature because most of the time some labs record the videos without methyl cellulose. And also pip install math. This is a math library contain the algorithms and some of the calculation for the blood flow analysis we can use, and numpy that is already famous we use for the calculation, matplotlib for the graph design, and the pandas that is module that we use for the pip install like command in our CMD for the importing of the respective libraries. And the install regex used for the backward and front, like you have the characteristics and then you can save it in the specific format. And also the pip install thread pooling that is used for the relative parallel processing that most of the time, and also to manage the speed of the processing, because in blood flow especially there are a number of challenges, so we have to get time limit as well as for the accurate result for the end of the video, because the algorithm take much time for the calculation. So the thread pooling we used to speed up the processing. And also this is the concept that we use in some of the distinguishing environments, so we can say that it's our simple work. Now this is our operation flow that for non-expert users, that simply you can create the folder having the videos like dorsal aorta and with zebrafish and medaka, download python, open command window and copy and paste the path. I will show it this later in next slide. So by using the command line you can simply get the selected ROI of the dorsal aorta in a separate window, and that will be a window for the better view that I mentioned for the this is the features like we used for the Python by use for the masking as well as for the stabilization. And now this is the view. I think it's clear for you guys to understand that there is the code file I mentioned. So you must check that you place the code file in the respective folder, then copy the path folder and then paste in the CMD. This is the simple you can use, and by using the control C or yeah, whatever you like. And the command to run the program, this is C command. This is actually the name that we select for the file of the code. So this is the point that you must be careful here, that two separate scales I mentioned in the first second slide that we introduced for the medaka and zebrafish. If you select the 0 or the you select the wrong one for the wrong fish, you will get the wrong result. So 0 is for the zebrafish and 1 for is for medaka. So both fish have different blood flow, that we have threshold set plan according to our previous published study based on the images. So we did set the scale according to that parameter. So if you select the wrong value, you will get, or the videos like you select medaka and you select the scale for the zebrafish, then you will get the wrong result. Then you have to press the space key, that is very commonly used to proceed, and you will see the two different windows. One is masked with selecting automatic ROI for dorsal aorta, and you can get the visualization here, and the process is ongoing. The video is running in your system. You can say that you can see the display, and also this is important that how you can say about the processing for the automated ROI, because most of the videos, if you have poor videos or low quality, I mentioned in the limitation of this tool that somehow it will select the wrong or the up. We do not say wrong the upper or lower side of the dorsal aorta, but it would not affect the velocity. The simple ROI may affect the blood cell count if you have poor resolution or poor quality video, but it would not affect the velocity of the blood flow. So this is the feature that must be you understand for using, and because most of the time we have different resolution type. And then video stabilization, this is the concept that I presented for you people. If anyone can use, or the unprofessional programmer can get practice that video stabilization. There are three types of built-in OpenCV based modules approaches involved for the mechanical video stabilization, for the optical flow video stabilization, as well as for the digital video stabilization. So here you can see that mechanical image stabilization used for most of the concern like special sensors like gyros and accelerometers that move with the image to compensate for the motion of the camera. And the optical video stabilization that I mostly recommend, that based on the stabilization that we achieve for the moving parts of the lens relative to the camera. So this is very I think good approach, that you can get the length of the light as it travel through the camera's lens, and it's more good. And then is the method does not require special sensors, that is called digital video stabilization, and it based on the motion estimation, motion smoothing, and image composition, that actually based on the parameters of the consecutive frames, and also the to filter about the motion, and that lasting for the stabilized in the reconstruction. So these are the three commonly practiced and traditional approaches for the video stabilization that are used in different languages like Python, MATLAB, and all that. So in OpenCV based libraries we have this. So video stabilization script that I used for in this study, you can see that this is simply based on the with stab function, and we did use, and then the followed by the other modules like pooling and all that. And also I mentioned for we targeted about the blood flow, so I included the fine blood line feature that you can see that how it works. And then also the important is the masking that is performed on the dorsal aorta precisely, because if we focus on the two blood vessels, then might be the data will be overlap and the result would be not good. So our target was to select dorsal aorta first. So by using the make title mask function, and also the proportion it set according to the window shape and size. So and the rectangular area was defined, and you can see that it depends upon the logic that whatever you use, it depends upon the programmer. And also that how you can see that the process being involved, like for the grid sizes, for the specificity of the relative image crafting, and especially on the pixels like grayscale and all that. So this is the masking concept that easily is understandable, and you guys also can use if you like for the stabilization. And after the automatic selection of the ROE was the challenge, because dorsal aorta. Sometime we have different positions in the moving of the video, if you especially we have shaky videos. So get ROI module we used, and the approximate size of the dorsal aorta were defined. Here you can see that by using the range from the image size and the shape we presented, and the pixel ratio did set, and then we converge the specific area to get the to set the ROI automatically for the feature of the dorsal aorta. And this is the nested loop feature. So we use the nested loops like for loop, and then we incorporated for the relative index to get the mask window with the relative automatic ROI selection. And most of the time we have a good result. So by calculating array data, here you can see in a specific ROI that we have defined about the index. So there is simply numpy based index feature we used, and stride function, and the tuple we used for the consecutive frame analysis, because I mentioned that we used for the frame differences like the optical flow. So this is our main concern feature that we applied in this study, and the point array and the append for the point to point frame direction. That if this is the video that is moving for the horizontal, and then the calculating for the blood flow Farneback algorithm. Here you can see the module is used to calculate optical flow Farneback, and you can see that how the processing is being involved, and detailed is mentioned in our study. And also that the basic OpenCV modules are incorporated, and the relative mathematical computation was involved. And then we focus about, this is the main script, this is the not whole script. So this is the just chunk of where we are using the algorithm. And every step you can see that most of the time the scale definition was very important, the resizing of the frames and the consecutive frame differences, as well as the point where the cell are being integrated, that movement in the subject, that it counts for the moving objects. In this case we have blood cells. So this is very important, that how we can develop our logic. It depends upon you guys, if you like to develop your logic and for the processing. And there is the also challenging phase is the oscillation graph, because it's not much easy that you can see here in the slide. It was a hell of challenge, because every time oscillation become disturbed due to the differences, and also especially in case when we have the fish movement, like the blood flow analysis based on, and the graphical representation during the recording, be that both are different things. So we have to target both to settle that. We have to check the moving objects as well as to get the oscillation based per frame, like the relative frame differences and the movement and that is the unidirectional. So this was very challenging. Every time I did repeat number of scales, that here you can see the ratio for the 30 fps I mentioned for the frames, and I tried number of different aspect ratio, and then finally we computed according to the relative the shape of the window, and also for the RGB levels that graphing we used, because this is very important to get the relative index. And also the uh, based on the color of the background, like moving objects we have white and black background in case, then it's more easy that we can use the RGB. But if you have different colors or you have different pixel ratio, then definitely you have to check according to that. And this is the script that to get the average blood flow velocity. So every did we computed according to to the whole time, that for we mostly have 1 minute and 6 second video, around 1 minute we have videos about the blood flow analysis. And using numpy we set the float values for each cycle, like for the each cycle mean that blood floating, and then the specific rotation is completed for the one mean flow. And then by calculating the float and the incorporating with the relative of the index value as well as the pixel value, and also for the Gunnar-Farneback algorithms approach to get the average of the blood flow, and then average of the blood cell count that we used for the counter selection. The counter is basically you can say the edges, and would used to calculate like we have different shapes like square or circle or like that. So here is the basic concept that you can use for the area that we detected. First manually I checked, and then I used some different filter level scales, that how it can be integrated for the relative motion of the blood cells. That we can, it was challenging as compared to velocity, because blood cells are still, it's challenging that we cannot detect 100% accurately due to the continuous motion, as well as due to the pixel and the resolution and all the features, because that cannot be uniform every time. And also blood cells, as the continuous, and later I will explain that we get average from the total count as the duration from 1 minute, like 1 minute and 6 seconds. So the cells are passing, and you can see the directional flow is being counted with the respective edges. So here counter was defined and by using OpenCV modules, and you can see the, now the results is, you can say, we get the average like in millimeter per second, average speed of the blood flow 0.29, something like that. And then uh, second is the blood cell count graph. So here you can see 76 and 893 like value. I mentioned that we did use the average count. So average count mean that the total count mean the total duration of the video that cell passing in the ROI, and the average that from the total the algorithm computed that are passing in first shift to the relative index. So the red line displays the average millimeter per second blood velocity, and then second is the red line for the average display of the cell count. So this is the basic feature that you can say being involved in our study. And it's quite interesting, but as well as very challenging, that because blood cell count is based on that is still challenging. And smooth oscillation, we use some filters, like basic concept was the logic design for the Gaussian and the baseline filters, and also for the differences in the spatial inferences and oscillation for the floating of the objects. And finally the designing of the numerical customization, that for to get the precise oscillation, because the oscillation always get disturbed, that I'm saying it was very difficult to get the smooth oscillation in the first go. So we did apply different approaches in that, and the logic design basically involved in this study for the blood velocity. You can see this is the already established parameters. This is not established by me. I mentioned the reference. You guys, if you are interested, you can get the reference in from next slides, and then you can see and get the logic. So basically, in blood flow, especially in Gunnar Farneback algorithm, we have the dense optical flow, and based on the polynomial expression is we can compute them mathematically. So the mathematical modeling concerns was involved. So it used the dense optical flow, because I selected this algorithm because blood flow is based on viscosity. So viscosity is determined with the relative, you can say, the dense object orientation, and the moving objects in dense pathway is more difficult, and its computation relatively slower than the Lucas candidate. Similarly, the logic design for the counter detection in OpenCV is the logic that I built for the 30 FPS videos for the medaka and zebrafish. And manually I selected first, and then I used the approach for the counter selection, that is based on a simple OpenCV version. Like if you have 3.2, you can get the module, and you can get the relative threshold values. And also, and this is important, that counter selection, that you must be set the pixel value, like if you have white background, black background, and white and black background, and background based on coloring scheme, that you must be careful about the selection, because this is important. If you miss that, then counter will be not be accurate, and you might get some confusion. So this is important. Also the accuracy based on in binary image, mostly like that for approximation in the counter selection. So this is the approximation method, that how counter work. I added the reference. If you people get here, you can see the four edges, let how counter work. The blue dots you can see in the second right side of the image. and this is the algorithm that we use. Like the three basic, you can say the basic steps were the scaling, input path, and information saved that we use for the algorithm approach. And using the OpenCV, in our case, we use the 30 fps video dataset to use the calculate the optical flow, and in our case the blood flow. And then this is the starting of the point index from the first frame, and then you can see the proceed for the per frame in the two consecutive frame reference of the distance, basically displacement. And then the input part, it means that it describes the video that to be used for this calculation, and then must be stored, the data must be like the calculation must be stored in the specific output path that is called is in our case the oscillation, and the information that is saved on the basis of the specificity. And then the key features of this program is the blood flow velocity measurement. Is simply you do not need to